Thank you very much. So I'm also a mathematician, so this will also be kind of a mathematics talk, but I hope you're fine with this amount of mathematics in your life for today. So I do algebra, and here are some words on the blackboard, and I kind of live in the world of words on the left, like algebraic statistics, and in particular maximum likelihood estimation, and I think most of you live in the world of the words on the right, like scattering amplitudes and CHY equations. And in this lecture, I will kind of try to connect those two worlds and to explain how you can use fairly classical algebraic methods to solve problems in physics to actually compute a very concrete scattering amplitude. So our goal is to algebraically compute the CHY amplitude. So that's the, I think, phi-cubed scalar 3-level amplitude. And in the first half of my talk, I will talk about mathematics. There will be a lot of mathematics. Hopefully, it will not be too difficult. If you have questions, of course, ask right away. And in the second part, I will indeed try to bring some physics into the game and explain to you why we needed all this mathematics that I'm going to set up now. So let's start with the mathematics. So K for us is a field. And actually for today, there's only two fields. It's either the real numbers or the complex numbers. So when it's clear whether we work with real or complex numbers, I will just write RC. When it's not clear and kind of the setup works in both cases, I will just write K, and that's what I mean. Okay, then the normal R is the ring of polynomials in n variables over the field K. That's the polynomial ring. Polynomials are just linear combinations of monomials with coefficients in this field K. So I think we all know that monomials look like this, and then so that's a monomial, and then polynomials look like this. So we can combine the monomials and multiply by coefficients. And in algebra, we say that this is a ring, which means that you can take sums of polynomials and still get polynomials, and you can multiply polynomials and still get polynomials. And you can subtract polynomials and still get polynomials, but you cannot divide polynomials always. Sometimes you will not get a polynomial. It's a ring and not a field. Okay, so those are very basic algebraic objects, and now we'll define some geometric objects. I will draw a line here. So the first geometric object we are going to define is an affine algebraic variety. So an affine algebraic variety in K to the n, so in the n-dimensional vector space over the field K, is the solution set of a finite system of polynomial equations. So Fi of the variables x1 through xn, there's as many variables as the dimension of this ambient space, equals to 0. And there is finitely many of those equations. So I wrote finite here in parentheses because actually this is not a necessary condition, but it's a very important fact in algebra that if you have an infinite system of polynomial equations, you can actually pick a finite subset and get a finite system which is equivalent to your original infinite system. Okay, so algebraic varieties are fairly special geometric objects. As the name suggests, they can be studied using algebra. And why should we care about algebraic varieties in the context of this workshop? Well, because this workshop is on positive geometry, And the central mathematical object in positive geometry is a positive geometry. And positive geometries, they live inside algebraic varieties. So this is basically the starting point for a mathematical definition of a positive geometry, which I will not give today, but still, those objects are very important in our story. And in a moment, we'll have some examples. And hopefully some of them will be familiar for you. So we have defined affine algebraic varieties, and affine algebraic varieties live in affine spaces. So this is kind of the affine space. And that's why they're called affine. But somehow in physics, the more relevant varieties are the ones living in the projective space. So let me define them now too. A projective algebraic variety. I think I was told to write a bit lower. Okay. A projective algebraic variety, as it follows from the name, lives in the projective space. So in the n-dimensional projective space over K. Is again the solution set of a system of polynomial equations. But those polynomial equations have to be special. It's a system of homogeneous polynomial equations. Polynomial equations. And we'll still denote them by Fi. So Pn has homogeneous coordinates. There's n plus 1 of them. So we start from x0. And then we go to xn. And we still kind of have a finite system of polynomial equations. So the key difference between those two definitions, apart from the ambient space, is this word homogeneous. And this has to do with the structure of the projective space. So let's try to understand why we have to require homogeneity here. So homogeneous polynomials, I'm sorry, I didn't tell this, are polynomials in which all monomials have the same degree. So all monomials have the same degree. Same degree. Okay, so why do we want our monomials to have the same degree? Why cannot we solve equations like, so x1 plus x2 squared is bad? Why can't we solve equations like that? This is because homogeneous coordinates in Pn are only defined up to a common scalar. So these two vectors of homogeneous coordinates define the same point in Pn. And this is because mathematically, the projective space is the space of lines through the origin in an n plus 1 dimensional vector space. So you can take any point on the line, there's a one parameter family of them, and each of them will represent a point in the projective space. So we have this ambiguity. And then we want to understand what it means for the polynomial to vanish at a point in Pn. So naturally we want, yes?
Just to be sure,
yes. Thanks. Okay, so we want this. We want our polynomial to vanish if and only if it vanishes in any scalar multiple of this point. And again. And this is the defining property of homogeneous polynomials. So homogeneous polynomials are precisely the ones that satisfy this. Because if a polynomial is homogeneous of degree d, in every monomial, when you scale the variables, you get an extra factor of lambda to the d, and then you kind of can carry it out, forward, and get the original polynomial it started from. And it's still going to be vanishing. No, you have to scale them simultaneously. It's very important. Okay, So those are the two definitions. We have projective algebraic varieties and affine algebraic varieties. Those are the simplest varieties. Those are also fairly simple compared to the general definition, and we will concentrate on these ones. We'll concentrate today on one particular variety. But let me start from some basic examples, very basic examples, to something completely not scary. So this is a variety, for instance, something that's defined by the equation x1 equals x2 squared. This is a parabola, a curve we have all seen in high school. And this is a variety. What can we do apart from taking a look at the parabola? We can solve those wonderful equations. x1 equals 0 and x2 equals 0. So each of those equations defines a point in, let's say, R2, and the intersection of those two lines defines a line, sorry, in R2, and the intersection of those two lines is a point 0, 0. So points are also varieties. So some very basic algebraic objects are varieties. What's a non-example? Non-example is, for instance, the graph of the exponential function, right? x1 equals e2, x2 is bad. This is not a polynomial, and you cannot rewrite it as a polynomial. So this curve actually also looks very nice and very systematic. It's smooth, but it's not a variety. So varieties really are very special geometric objects. And, well, those are toy examples. Sorry? Oh, no, it isn't. It's an affine variety. Yeah, that is very true. But you can homogenize those equations. So in P2, this will look like this. We will introduce another coordinate, and then it will be a homogeneous quadric, but thanks. Okay, this is an affine variety, which is by itself not projective, but you can always kind of projectivize it. This is an almost projective variety right away. Both of those equations are linear and homogeneous. Okay. So this can be viewed projectively right away. Okay, so I told you we will have some more involved examples as we proceed. For now, this is just the toy setup. And I told you that algebraic varieties can be studied algebraically, so I would like to say a couple of words about this. How do we do this? So the key to studying them algebraically is a correspondence between geometric objects. So there's a correspondence between geometry and algebra. And more precisely, between varieties and ideals. And ideals are algebraic objects, varieties, as we have seen, are geometric objects, and we study varieties in algebraic geometry by studying their ideals. So let me define an ideal. An ideal, for us, in general, it works for any ring, but for us, it's a subset of our ring R, so of the polynomial ring. The subset is an ideal. So the name suggests it's a very nice subset if the following two conditions are true. So first of all, for any A and B in I, their sum is again in I. So it's closed under addition. If you have two polynomials in the ideal, you can take their sum and you will stay in the ideal. The second condition is that for any A in I and for any C in R, so we have a polynomial in the ideal and a polynomial anywhere in the polynomial ring, an arbitrary polynomial, we have A times C is in the ideal. So the ideal has this, so ideals have this nice consuming property. You start from an element in the ideal, and all of the polynomial multiples of this element will also be in the ideal. And why is there this correspondence? So a fact is that the set of all polynomials vanishing on a variety, not necessarily a finite, on a variety that is either affine or projective is an ideal. And let's try to understand why this is true. So first of all, it is clear that we have, for instance, this point example where we have x1 equals 0 and x2 equals 0. So it is clear that if there are two polynomials that vanish at the origin, their sum also vanishes at the origin. So this property is automatically satisfied. If two polynomials are 0 at a point, then their sum is 0 at a point. And this property is actually also satisfied. If one polynomial is 0 at a point, then whatever you multiply it with, it will still be 0 at a point. So ideals turn out to be a natural algebraic structure to study varieties. And this correspondence is kind of the starting point of algebraic geometry. And I will give you two more fairly abstract definitions that kind of connect to the story of varieties, that describe the basic properties of varieties. And then we will move on to more concrete things. So the last two abstract definitions that I will need for today's talk, there's the risky closure and the degree of a variety. So what is as a risky closure? So by definition, the risky closure of an arbitrary set S, not necessarily of a variety, so in Kn or in Pn, is the smallest, let's say by inclusion, variety containing S. So S itself may not be a variety. A good example is just a line segment. It's just some bounded set on the line, on the real line. But it's not a variety. There is no polynomial which vanishes on the whole thing. So the risky closure of this guy is the whole line. So there are no polynomials vanishing on it. The system is empty, and this means that by definition all ambient spaces are also varieties. So the risky closure is the smallest variety containing some set. The formal definition of the smallest variety is the intersection of all varieties that contain it. Okay, and the second formal algebraic definition, inclusion. So it's the intersection of all varieties that contain S. Okay. The second formal definition is the degree of a variety. But before talking about the degree, let me say a couple of words about the dimension. So varieties are geometric objects. They have a number that describes them called the dimension. There's a formal algebraic definition of this number, which I will not give to you today because it's long. But the dimension is really what you think it is. It's very intuitive. So a point is 0-dimensional, lines are 1-dimensional, planes in 3-space are 2-dimensional. And varieties are geometric objects for which you can also define this dimension. And once we know or have an idea of what the dimension is, we can define the degree. So this works nicely and non-abstractly, concretely only over the complex numbers, but we will also need this over the complex numbers today. The degree of a complex variety V of dimension k in C to the n or in the complex projective space is the number of intersection points of V with a generic linear subspace of C to the n, P to the n of dimension n minus k, of complementary dimension. So if you see this definition for the first time, it can be a little bit intimidating. So we have some number that is supposed to describe our variety, to describe some of its fundamental properties, But we do somehow a fairly non-obvious thing. We take our variety, we take some other geometric object, and then we intersect them and count the number of intersection points. So what is this about? So first of all, the choice of dimension here is very natural. If you intersect two varieties of complementary dimensions, you get a zero-dimensional set. So you really get a union of points, a finite union of points, and you can count this number of intersection points. So what the degree intuitively is supposed to tell you is how curvy your variety is. So dimension kind of answers the question, how big is the variety? And degree tells you how curvy it is, how kind of complicated it is. And this idea that degree is some measure of complexity will be very important as we move on. How curvy or complicated it is. And this generalizes the natural notion of degree for plane curves, for instance. So I have to go back there anyway. Yes, I'm going to. So let's come back to our parabola, right? It's a curve, and it's a quadratic curve, we know this. So this is a real picture, so I will draw a real line, and we can draw a real line that intersects the parabola in 2 points, and this 2 corresponds to the degree of this equation. Because this equation is quadratic, you will never get anything bigger. So again, this is a curve, this is a one-dimensional variety in a two-dimensional space. So in this setup, n is 2 and k is 1. So n minus k is also 1. So you want a linear space of dimension 1. This is a line. We intersect the parabola with a line, and we get 2 intersection points. Now I could have drawn, of course, this line. But as I said, that definition only works over complex numbers. But this line does not intersect the parabola in real points, but it has still 2 complex intersection points with the parabola. So in any case, for a line that's general enough, you will get 2 intersection points, and this is a constant number for general lines, and this is the degree of the variety. And again, for the case of plane curves, this is precisely the degree of the defining polynomial. And then in higher dimensions, this is a natural way to generalize this definition, the degree of a curve in the plane. Okay, so this, now I filled the board with abstract algebra, and this is, I think, the heaviest mathematics that we will have in this talk today. Yes? Yes, you cannot get more. So the generic number, the general number is the highest number. So special intersect lines can only intersect the parabola in a smaller number of points. So for instance, the tangent line here, the origin, intersects the parabola at only 1 point. So it can fall, but if your line is kind of general, it's not a tangent line, then you always get 2 points. Okay. And nothing to erase, the board is there, so I have to come back. But again, the main message that you are supposed to carry away from this board is that, okay, 2 main messages. First of all, varieties are kind of important in physics and in positive geometry. I have not yet explained why. I just waved my hands and said, well, positive geometries actually live inside varieties. And the second message is that varieties can be studied using algebra. So in the end, it all just boils down to studying the defining equations of the variety. And in particular, if you want to understand something about volumes, which is important in physics, and you can take a close look at those defining equations and do some non-trivial mathematics and actually understand something. So, but I think I will talk a little bit about this tomorrow. Today we will now move on to more applied mathematics, to statistics. And then from statistics we will move on to physics. Okay, so let's start with algebraic statistics. Algebraic statistics is an area of algebra, an area of applied algebraic geometry, in which one studies statistical questions by using algebra. And now I will try to explain to you how this works. So what's a general problem in statistics, for instance? The one that we can solve using algebra and the one that will be relevant for physics for today. So general problem will take a while to set up, but there's nothing complicated. So we'll start from a discrete statistical model. So in a discrete statistical model is some set is a set in, let's say, Rn, or rather Rn plus 1, describing or consisting of probability distributions. Describing some phenomenon. Those are very imprecise words. And what do they mean? So a discrete probability distribution is something I think most of you have seen. It's just a vector of n plus 1 numbers that sum up to 1 and that are non-negative. So this means that we have some random variable, we perform some experiment, and there's n plus 1 possible outcomes. Each of them has a probability, which is a number between 0 and 1, and they sum up to 1, because something has to happen in your experiment. Okay, and then a discrete statistical model is just, so every probability distribution is a vector of numbers, it's a point in Rn plus 1. We just take some set of probability distributions and say this is our model. In real life, this means that we conduct some experiment and we want to understand kind of what are the parameters that define our setup. And those parameters also define probability distributions, and we kind of observe some probability distribution and we want to understand which one of those theoretically possible ones we actually have in our experimental setup. So once again, I will try to write this down. We conduct an experiment or a series of experiments. We conduct a series of experiments. And obtain some probability distribution and observe some probability distribution. So what do we want to do with this probability distribution? The problem is that our experimental setup is noisy. The setup is noisy. Our experiments are not perfect. So our distribution is not really in the model, the one that we obtained. It's not one of the theoretically possible ones. But we know there is some noise. So what we want to understand? We want to understand what's the best distribution in the model describing our experiment. And this is known as maximum likelihood estimation problem. So we want to know which probability distribution, likelihood estimation, is the best for us, is the closest to what we've seen in our physical reality. And where does the algebra come in? So in algebraic statistics, models are described by varieties. So our sets, our statistical models, come from varieties. So I will write MC, meaning that it's a complex variety, is a complex variety. And our model M is the intersection of this variety with the probability simplex. So this is the probability simplex. So positive numbers, no negative numbers that sum to 1. And this can be interpreted projectively. So projectively, we have a projective variety, and the simplex can be identified with the positive part of Pn. Yes? Was that a question? Yes. 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 Okay, so we can interpret this projectively because, again, the probability simplex is defined by a bunch of positivity inequalities and one equality, which says the coordinates sum up to 1. Projectivizing means that we forget about this equality, that the coordinates sum up to 1, because if we think about them projectively, their sum is not a meaningful thing. We can scale them all simultaneously and get any number instead of 1. So the correct projective analog of the simplex is the positive orthant of the projective space. So the space where all homogeneous coordinates are positive, which means they have the same sign. Okay. So we will be interested today in parametric models. I started from defining varieties as sets that come as solution sets of systems of polynomial equations. So you can describe your variety by equations, but you can also describe your variety by using parameterizations. So parametric models come from nice varieties. So in this setup, parametric models, MC is the risky closure, the words that were important to us like 10 minutes ago. So this is the risky closure of the image of a rational map. And the rational map is just a map that is given by rational functions. I will tell you what this is in a moment. So the map goes from C to the M to P to the N. So M and N are two different numbers. Can you see this? You can see this, good. Okay. So what's the rational map? A rational map is a map given by rational functions. In C2. So this point, sorry, for y in C to the M, this point is in Pn. So these are rational functions. Rational functions are ratios of polynomials. So this is a numerator over a denominator. This is a polynomial, this is a polynomial. Now you can plug in any complex number and you'll get a number here and you'll get n+1 numbers like this. And as y goes over all points in Cm, those points will go over a subset of points in Pn. N is normally greater or equal than m. Okay, this you cannot really see. Hopefully you can. N is greater or equal than m, so we take Cm, we do this map, and we again obtain something normally m-dimensional inside a higher dimensional space. And because those functions are rational, they're ratios of polynomials, there will be a lot of algebraic relations holding between those functions. So we will actually get a variety. But how does this? Yes. This one. Okay. So we start from a complex variety, a set defined by polynomial equations. But our model is a set of probability distributions. So we take all points in our variety which are actually probability distributions. So we take all points in our variety which have non-negative entries that sum to 1. And this means that geometrically our model is the intersection of this probability simplex and some variety. So inside the simplex it's defined by polynomial equations. And then projectively you can replace the probability simplex with the positive orthant of the projective space. Why does this work? Here you have two constraints, an inequality constraint that every coordinate is non-negative, and an equality constraint that they all sum to 1. So this is affine. Saying that all the coordinates sum to 1 is perfectly normal in like a normal coordinate space over R. In a normal vector space over R, sorry. And then if you want to think about those things projectively, requiring that the coordinates are non-negative is still perfectly fine. You can do this. But you can no longer say that they sum up to 1 because each individual coordinate is not a well-defined thing. So the vector of coordinates is only defined up to a common scalar, which means that you can multiply all of the coordinates. So you have this constraint. But in projective space, this coordinate can be replaced with lambda, and this can be replaced with lambda, and here you get lambda, an arbitrary non-complex number. So this constraint projectively becomes degenerate. We can forget about it because it's not meaningful. It says our coordinates will sum up to something. That's of course true. Yes? Yes. It's a special. I mean, yeah, the domain of applicability of algebraic statistics is somewhat limited. We choose to work with the models that are defined by polynomial equations. Of course, not every statistical model that comes from the real world is such a model, but many are, for instance, Gaussian statistical models and can normally be described by some polynomial constraints. But really, this is not complete statistical generality. This is a fairly special setup, but again, the model that will be relevant for us in the context of physics is such a model. So I'm just trying to set up the math. Okay. So what does this all mean? We have a model which is parametric, so it comes with a parameterization. Each point is the image of a point in an unconstrained space under some rational map. So there are constraints between these points. So there will be polynomial constraints. There will be constraints between on the coordinates. And we cannot circumvent those constraints because, as I said, we map Cm, a lower dimensional thing, into a higher dimensional thing. We get a lower dimensional thing inside a high dimensional thing, so there have to be constraints which define this lower dimensional thing inside the high dimensional thing. So parametric models are important for us. And maybe in 10 minutes, we will concentrate on one very special parametric model. Now I'd like to explain why in this setup, the maximum likelihood estimation problem is an algebraic problem, which also can be described by polynomials. So suppose we conduct an experiment, right? There are n+1 possible outcomes in our parametric model again lives in p to the n. This means that there is n+1 possible outcomes. So we conduct an experiment with n+1 possible outcomes. And what we want to do, we want to record the outcomes. We have a series of experiments, so many experiments, and we observe frequencies 0 through un. This is how many times we observed the ith outcomes. How many times we observed each outcome. And then we want to, from this vector, we want to recover a distribution. We want to recover a distribution in our model M. distribution in M. And M for us is a parametric model once again. M comes from the variety MC, which is defined parametrically. So what does this desire to reconstruct a distribution mean mathematically? Mathematically, we want to maximize a rational function. We want to maximize the log likelihood function. Likelihood function. So the log likelihood function LU is the logarithm of P0 of y to U0 Pn of y to the Un, and we normalize by the sum of the coordinates P0 through Pn raised to the power U0 and so on plus Un. Okay, so now let's think about why this actually is supposed to recover a nice probability distribution. Those numbers are kind of, in the statistical context, supposed to be between 0 and 1. They're the small numbers, and we want to find a distribution which kind of maximizes this function. This means that the higher this number Un is, the higher we want to be the probability of each individual factor, because then the result will be bigger. So the intuition here is that kind of we are looking for a distribution in which the probability Pn is high for this when this exponent is large. And this was a bit hand-wavy, I understand, but really mathematically, maximum likelihood estimation problem reduces to maximizing this function, but then we can take the logarithm because the logarithm is a monotone function. So maximizing this is the same as maximizing the logarithm. The maxima of the logarithm are exactly where the maxima of this thing are. And we want this, I mean, yes, basically in this setup, we want to just find the y, or alternatively, we could forget about the parameterization and just say, well, we want to maximize a function of formal variables, P0 through Pn, such that the vector of variables is on our variety. So really, the main constraint is that P0 through Pn is in our model. And in this setup, with parametric models, this constraint kind of becomes degenerate because you work in the space of y coordinates, which parameterize your model. There are no constraints, and it's an unconstrained optimization problem. So why did we take the logarithm? Why is it nicer to take the logarithm from the point of view of algebra? Intuitively, this is a weird decision because, this was a rational function. We like rational functions and polynomials in algebraic geometry. We don't like logarithms so much. But we don't want to compute the value of this function. We want to minimize it. And if we minimize it, we want to solve critical equations. So we'll have to take the gradient of this function and kind of minimize this. So maximize this, sorry. So anyways, we are looking for the critical points. So maxima of LU are given by critical point equations. And the critical point equations are what you think they are. We take this function, it's a function of many y's, and we take the partial derivative with respect to each y, and we want this to be 0. We want to solve a system of equations, and the equations are partial L over partial yi of y is 0. But this, the derivative, the logarithmic derivative, is actually a rational function. The sum from 0 to n of uj where y is in Cm, and outside of some special space in which those functions vanish. So we want this rational function to be well-defined, and D is the set of points in Y on which this is not well-defined. So this is where any of those guys are not well-defined. So we throw this set out. So in the end, to solve the statistical problem, we can use algebra. We can solve algebraic equations. And we want to measure complexity of the system. In practice, of course, you will solve those equations numerically. And when you solve those equations numerically, a priori, you don't know how many solutions they have. So you need this data, you need this information about how many solutions there are in order to be able to actually numerically solve them and be sure that you found all the solutions. So what you do is you solve this over C. Again, we kind of make our problem algebraic. We forget about the real world context, and the real world context was that those numbers are positive, real, and sum up to 1. We forget about all of this. We forget about the fact that these guys are actually positive integers. Everything becomes complex numbers, so everything is as general as it can be. And we are looking for complex critical points, so complex solutions to this system. Which denominator? Okay, yes, there is this one more term, which, okay, I'll just let myself write plus dot dot dot, but really this will correspond to the derivative of the denominator. Again, projectively, because this kind of sums up to 1, you could forget about this, but really it doesn't matter so much. So yes, it's best not to forget about this. I did, and this was bad. So plus log derivative of the denominator. But this is, again, of course, a rational function, so this doesn't change our setup. Denominator. Okay. So as I said, we think now we make our problem algebraic, and we think everything is complex. Everything is in C. And if we do this, there is a notion of complexity, a notion of degree. So the number of solutions to the likelihood equations. So these equations are known as the likelihood equations. Let me take a chocolate color. I'm disrespecting the lines that I drew myself. I hope that's okay. But those are the likelihood equations. And over there, you can see that those correspond to scattering equations in physics, and we are getting to the point where we will hopefully see this. Okay, so these are the likelihood equations, and the number of solutions, of complex solutions, the likelihood equations is constant for, oh, this is bad, okay, for generic values of this U variables, which were supposed to describe the data we observed. And this number is called the maximum likelihood degree. This number is the maximum likelihood degree of MC, of the variety that defines our model, and also of the model. So again, we have some notion of degree, which is different from the classical notion of the degree of a variety. This is because when we define the degree of a variety, what we did was basically we tried to solve a system of linear equations on the variety. This is what intersecting with the linear space means. And here, our equations are kind of special. They are not general linear equations, and this number is in general not the same number as the degree of a variety. But in the physics context today, we will also want to solve these equations. And this is, therefore, the correct invariant to look at. And the ML degree measures, it's a complexity measure, so it measures the complexity of solving scattering equations. That's a complexity measure. Okay. Now I will try to start going towards physics. I realize this was a lot of math, and you're probably tired of math, so I will do my best to minimize the amount of math in your life in the next 40 minutes. But there will still inevitably be some. So let me maybe do one more purely mathematical thing very quickly, and then we will immerse ourselves into context. So I defined affine varieties and projective varieties, but there are better varieties. There are just affine varieties and there are very affine varieties. And the variety which appears in this context is a very affine variety. So the story of very affine varieties, which will be very short here, starts from the following fact. The algebraic torus, which is the space C without 0 to the n, is a variety. Now, if you take a look at this, originally this is a very counterintuitive fact. We say that varieties are defined by equations. Here we define the set by inequalities. We said xi not equal to 0 for each I. So this is not an equation, this is an inequality. So this kind of should not be a variety. But the trick is that this is not a variety in C to the n. This is a variety in C to the 2n. And how does this work? Well, if xi is not 0, then 1 over xi exists. It's well defined. So really, you can represent any point x1 through xn such that all of the coordinates are non-zero in Cn as a point in C2 to the n, where the first n coordinates are the same as they were, and the last n coordinates are the inverses of the first n coordinates. So it took n coordinates, and then we inverted the n coordinates. And now this parameterizes an algebraic variety, right? Your equations are, well, kind of, let's call the second coordinates y1 through yn. And the equations that cut out the torus are xi times yi equals 1. So we took this torus and we embedded it into a higher dimensional space where it is manifestly cut out by algebraic equations. So the torus is a variety. And a very affine variety is a closed subvariety of the torus. Yeah. Okay. So the definition: a very affine variety is a closed subvariety of the torus. So it is a variety itself which is contained in the torus, and it becomes a variety under this embedding. And very affine varieties are nice, as follows from the name. And the kind of idea behind the name, I think, is that a projective variety lives in the projective space. To get the affine space, you remove one hyperplane from the projective space, the hyperplane at infinity. And to think about very affine varieties, you just continue removing hyperplanes. So you remove all of those hyperplanes, all of the coordinate hyperplanes. And if you still get a variety living inside this space, it's a very affine variety. And again, as I said, removing hyperplanes is a good idea. So the main example is a hyperplane arrangement. So a hyperplane is just a linear space of dimension n-1 in the n-dimensional space. The hyperplane arrangement, Oh yes, yes, C star is C without 0, exactly. Usually I write C star. I wanted to do this very clearly here, and then I forgot. But yeah, C star is the invertible elements of C, so everything that's on 0. Okay, so the main example are hyperplane arrangements of M greater or equal than n hyperplanes in C to the n. Well, n hyperplane, you can remove n hyperplanes, and this will, 1 second. You can remove n hyperplanes, and this will correspond kind of to removing the coordinate hyperplanes. You can do a coordinate change under which they become coordinate hyperplanes, and you get the torus, and you can continue removing the hyperplanes, and you'll still get a variety. Question? Yes? This one. Yes. It's a good question. I am not sure. I think this is the most natural dimension, and then in the end, you just want to know that this is the dimension. But I don't actually think so. I'm not so sure, but I would probably say no, because then you have n independent coordinates, and you want some more coordinates which kind of connect to those. So you have to produce like some more coordinates from these ones to tie them. I think this is the most natural way to think about the torus as an algebraic variety. There's no benefit in trying to like embed it into a lower dimensional space. Okay, so let me draw a picture. Hyperplane arrangements look like this. And complements to hyperplane arrangements are varieties under this interesting embedding, or under similar embedding. And what we will do now is we will concentrate on a very, very special, very affine variety, which is the moduli space M0n. But before doing this, one last theorem. Very affine varieties are nice for algebraic statistics because the ML degree for them is a very well understood number. So it's a special feature. It's a theorem by Chuniha from 2013 that if X is a very affine variety which is smooth, so there are no weird things like this, so things like this are bad, there are no singularities, it really looks like a smooth geometric object, then the ML degree of X is the absolute value of the topological Euler characteristic. So this is the topological Euler characteristic. This is a very classical topological invariant, so this is something that can be computed in most cases for varieties algorithmically, and the ML degree is really just the absolute value of this. This is a very strong theorem, and we will apply it again to one very particular variety. Not necessarily, as I said, an arbitrary hyperplane arrangement will give rise to a very affine variety. The way you can think about it is that you can perform some coordinate change which can turn them into something that looks like coordinate hyperplanes. But this is not a constraint, so you do not really have to throw out the M coordinate hyperplanes. It can be arbitrary. Because in a sense, if you're on a plane, you can forget about your coordinate system, right? Just draw some hyperplanes in a coordinate-free thinking. So there is no constraint that those are really the coordinate hyperplanes. Okay, so if you have a very affine variety, for instance, the complement of a hyperplane arrangement which is smooth, then the ML degree of this variety, the ML degree of that statistical problem which comes from this variety, is the absolute value of the topological Euler characteristic of X. So this is a classical mathematical invariant. I'm not going to tell you what this is right now, but this is some number that's well understood. This is not some number that we are interested in, a priori not connected. The theorem says they're actually the same. There is some involved math going into this. What is it? Oh, I have chosen not to tell you, and I will not. The definition is this is a classical mathematical number that we all like. I think this is the level of details that's necessary for today. Mathematically, it's the alternating sum of Betti numbers of the variety of the dimensions of singular homology groups. Like you're familiar with homology theory, that's what it is. But yes, I will not explain to you what singular homology is. Instead, I will try to use my remaining 20 minutes to actually do some physics as promised. So we want a very special towards physics. We will take a very particular variety, a concrete variety, M0n. So M0n is, I think, called the worldsheet in the, or some part of it is called the worldsheet in physics. So I will leave those words on the board. And what is the moduli space? Well, first of all, what's the concept of moduli spaces in geometry? Moduli spaces are geometric objects whose points parameterize other geometric objects. So you have some geometric object, it's represented by a vector of coordinates, and you use those numbers to kind of understand something about a different family of objects. So the Grassmannian, which Melissa talked about, is an excellent example of a moduli space because the points in the Grassmannian correspond to k-dimensional linear spaces in the n-dimensional space. So each point represents a geometric object, and so geometric objects are kind of the same kind. They're all k-dimensional subspaces, but they're different, and you use the structure on this variety to kind of understand which one is which and how they're connected. And we will do something that's very similar to the Grassmannian. We will do the moduli space of n points on the projective line. So this is the moduli space of n distinct points on P1 up to the action of the projective linear group. It's 2x2 matrices. So what does this mean? We are on a projective line, we have a configuration of n distinct points, and there's kind of a coordinate system. And we can do automorphisms of the line, right? We can move points in some direction, and the way they are located with respect to each other will not change. Just their general location on the line will change. And we don't care about this. So this quotienting operation, when we say, well, two configurations are the same if they're related by the action of PGL2, the projective linear group. So we do this in order to kind of explicitly tell that we only care about the relative position of those points and not about where actually each individual point is on a line. And now I will give a concrete description of this variety, and then we'll move on to scattering equations. So what's the concrete description of this variety? First of all, okay, that's the modular space. I have not defined this, but this is a very affine variety, and I will demonstrate this in a moment. So the theorem M0n is a very affine variety of dimension n-3. Variety of dimension n-3. And this -3 kind of comes from this action. This means when we quotient out by the action of this projective linear group, we can fix 3 points, and then the remaining n-3 will be the free parameters. Sorry, what do you mean? So points in the projective space are represented by vectors of homogeneous coordinates. In P1, there's 2 homogeneous coordinates. You want to act on a vector of 2 coordinates with a matrix. This matrix kind of has to be 2x2. So I'm not sure I understand the question. Yes. I don't think so. So again, this is as low dimensional as it gets. P1 is a line. If you have 1 homogeneous coordinate, you just have 1 point. It doesn't make sense to consider point configurations on 1 point because there's just 1 point configuration. So there's like no mathematics there, basically. This is the simplest setup, and in the simplest setup, PGL2 is the group of matrices that acts on points in the projective space. Okay, so M0n is a nice variety. It's a very affine variety. It's a smooth very affine variety of dimension n-3, and let's quickly try to see this. So let's quickly try to, first of all, understand what are the concrete representatives of points in M0n and why this is a very affine variety. Okay. So how to think about M0n concretely? Well, in terms of 2 by n matrices. Each point, so each column represents a point in P1 that's a vector of homogeneous coordinates. There's n of them, and when we factor out the action of the projective linear group, when we account for the automorphisms of P1, we can say that we fix 3 of the points to be 0, 1, and infinity. So on the level of those matrices, this means 0, 1, 1, 1, n-3 free parameters, and 1, 0. So this is the point at infinity, this is 0, this is 1, projectively. Okay, and we have n-3 columns that are free. What we know is that, again, the columns contain homogeneous coordinates of each point, so we have some scaling freedom. So our scaling freedom can force all of those points to have the second homogeneous coordinate to be equal to 1. We know that the points have to be distinct, and we know that the point at infinity is already here. So those are not at infinity, which means that the second coordinate is non-zero. And then we have n-3 degrees of freedom, and this n-3 is that n-3 in the theorem there. So these entries kind of parameterize our variety M0n. Okay, but why is it a very affine? So we kind of understand it's a variety. Why is it very affine? This is because M0n is identified with a hyperplane arrangement complement. A hyperplane arrangement complement in C to the n-3. So we will kind of call these guys sigma 1 through sigma n-3. And what are our constraints? We don't want sigma I to be 0 because 0 is already here. We don't want sigma I to be 1 because 1 is already here. And we don't want sigma I and sigma j to be equal because by definition we want configurations of n distinct points. So we have all these hyperplanes. In total there is n choose 2 minus n of them. And well, M0n is the complement of this, right? We just take all the possible values which are not 0 and 1 and which are different. So we realized M0n as a hyperplane arrangement complement, and this is a very affine variety. And this means it's a very affine variety. Now I said it's a variety, we would like to understand what, yeah, oh sorry, yes. Oh, okay, sure. So again, points in the projective space are given by homogeneous coordinates. On P1, there is 2 of them, x0 and x1. You can choose any representative in this class of proportionality. So x0 and x1 is the same as lambda times x0, lambda times x1. So then geometrically, P1 is C plus 1 point, which we conventionally denote as infinity. So how do we get C here? We can say, well, let's say x1 is equal to 1. So we choose this normalization so that x1 is always equal to 1. There's always a representative such that this is true. And we have a free parameter which kind of traces out C. But x1 could be 0. And if x1 is 0, there's a unique point. So if x1 is 0, we have complete freedom here to scale, and we only get 1 point. So when x1 is 0, we get an infinity. So this point, 1, 0, is kind of the infinity point in these homogeneous coordinates. And then these points are morally 0 and 1 because we forget about the second one coordinate and we see 0 and 1. All right. Okay, chances are I'm not going to solve the scattering equations today, but we will get very close to this. So M0, so again, in words, scattering equations are a method to compute the phi cube scalar tree-level amplitude. Scattering equations are likelihood equations on this model, on M0n. And then computing the amplitude is an algebraic procedure which starts with solving the likelihood equations and then doing something to the solutions. So in statistics, what we do is we look for a unique positive solution, which is actually a probability. So we solve those equations over complex numbers, and we know if the model is nice, there's a unique solution which corresponds to an actual probability distribution. We pick it and we forget about all the other ones. In physics, we do not do that. We really care about all the solutions. All the solutions will be very important. We'll probably see this tomorrow rather than today. But that's the general story. So that's why I put up all this math here to be able to formulate CHY equations and to kind of tell you what happens if we solve them. So I will continue with, so this is kind of physics in math already. It's directly relevant for a physical problem. And I will continue with this. So the last thing we want to know about M0n is that there's a nice system of coordinates on M0n, the so-called dihedral coordinates. So first of all, we parameterized M0n with those entries of this 2×n matrix. Now, it's 3 different sets of hyperplanes. So yes, and A not equals to J. Exactly. So those are the hyperplanes on which we do not want our sigmas to live. And well, so a sigma, the vector of sigmas is a point in Cn minus 3, and the bad configurations are the ones which are on one of those many hyperplanes. There's n choose to minus n of them. We throw them out. We get a hyperplane arrangement complement. Okay. So nice coordinates on M0n. Why do we want nice coordinates? Because we want our scattering equations to be nice. You remember that we worked with parametric models, and the simpler the parameterization is, the simpler the equations will be in the end. So our goal right now is to simplify our life as much as we can before we solve the equations. So first of all, we will introduce this notation. So the difference between sigma I and sigma j and sigma I, sorry, is this circle bracket ij, and the convention is that if either if this is infinity or if this is infinity, then we declare the difference to be infinity, and otherwise it's a finite number. Then we will introduce something called the cross ratio. This is just defined by this funny formula. So here we have 4 different numbers. So I, j, k, and l are pairwise different. So 4 different numbers. 4 different numbers. They're ordered and they define this cross ratio. So we have this bracket, this difference of sigmas for ik, for jl, for il, and for jk. So again, we come back to this original parameterization where we represent our configuration by a matrix with n-3 free entries. And we take those n-3 free entries, we cook up new functions, and then we cook up new functions from those new functions. And in the end, this is supposed to give you a nice description. And then the dihedral coordinates on M0n. coordinates on M0n are just special cross ratios. So here we have n choose 4 many, and that's a tone really, because the dimension is linear, it's n minus 3. So n choose 4 is again a very large number, and this is clearly a redundant description. So the dihedral coordinates on M0n are still going to be dependent, but for us in this framework of algebraic geometry, this is rather good, because we will know the relations, we will know the equations, we will see that this is an honest variety. So the dihedral coordinates are just very special cross ratios, which are defined by two numbers, I and j. So we take I plus 1 on the left, and j plus 1, j on the right. So here we have I plus 1, j plus 1, j. And I and j are non-adjacent modulo n. So I minus j is not 1, 0, or minus 1 mod n. And those coordinates are nice because they have a nice combinatorial meaning. I have 4 minutes. Excellent. Enough to explain the combinatorial meaning. And then we'll do the actual physics in 10 minutes tomorrow. Okay, so what's the combinatorics? The u coordinates, as I said, are indexed by two numbers, which are non-adjacent modulo n. This means that the coordinates are indexed by diagonals of an n-gon. Indexed by diagonals of an n-gon. Why is that? Well, you can enumerate the vertices of the n-gon. There's something happening here. By numbers from 1 to n. And the coordinates here are indexed by a pair of indices from 1 to n, which are non-adjacent, which means that if you draw a line between the two numbers in an n-gon, you will not get a coordinate. If you draw a line that is the edge of an n-gon, you will not get a u coordinate. But if you draw a line inside, a line that's at the diagonal of an n-gon, you will get a perfectly well-defined u coordinate. So in this particular case, the coordinate will be u13, and each diagonal indexes one u coordinate, and there's exactly as many u coordinates as there are diagonals. Okay, so this means then that the combinatorial description of the equations that connect the coordinates, the u coordinates, is nice. We can associate each equation to something that's happening inside an n-gon. J. Okay, so these are the equations that connect the u coordinates. How does this work? For each ij, we have a coordinate uij, and we want to connect it to the other coordinates. And this is very combinatorial. We add the product of all the u coordinates that correspond to the diagonals that cross a given diagonal. So let's do an example here. We have a 5-gon. 1, 3 is, let's say, 1 u coordinate. What are the diagonals that cross this diagonal? This diagonal and this diagonal. So we get plus u to 5 times u to 4 minus 1 equals 0. And then there is an equation for each u coordinate, and these equations form a complete system of polynomial equations that describe the relations between the u coordinates. So all polynomial relations between the u coordinates follow from these relations. And I heard the bell, so now lecture tomorrow we will wrap this up. We'll do the actual physics. We will use the u coordinates to set up a likelihood function or in physics a scattering potential to get the CHY amplitude. So again, tree level, scalar phi cubed amplitude for endpoints. So the endpoints are the n in M0n. And I think for today it's a good moment to stop. Thanks.
Thank you very much, Dmitrii, for this nice talk. Do we have more questions?
Okay, I have two questions. The first one is very short, which is over here, sigma I minus sigma j. You say if sigma I or sigma j is infinity, then they're different. But shouldn't those be complex numbers? Did I miss something?
No, absolutely. But in the projective space, exactly. And if there's two complex numbers, the difference is well defined. But the projective space is the complex projective space is the complex plane plus
right,
1
but
point.
You, to define the sigma i's, you sort of exclude the possibility that any of your points is infinity.
Yeah, that is true. That is true. A good
Okay.
point.
Okay, it's not a big thing. My other question is, so this is some connection between, or like you're telling us about a connection between a particular sort of instance of algebraic statistics and a particular scattering amplitude.
Yes.
I'm wondering to what extent it's sort of like about the particulars and to what extent you can sort of make
That's a very
analogy.
good question. I think it is to a very large extent about the particular case. I'm not aware of like many generalizations of this.
Okay.
I think first of all, the specificity of the Suvrat is kind of very physically meaningful, and it's really important to write in physics. And then solving these scattering equations on this particular variety gives you an amplitude, a very concrete amplitude, and I'm not sure if this has been like brought much further. It's maybe a question for physicists, but I really don't think so. So it's very specific and probably not very well generalizable.
We want our sigma and this hypothetical equations, they will always close. I mean, in a sense, like that will form a closed one.
Well, those are complex, and you're thinking about the real picture. If you take those hyperplanes, there will be bounded regions. If you take the real locus, so there will be many closed volumes, more than one.
That's it. Bounded. Yes. And my solution is lie.
What will lie inside that?
My sigma will lie within that.
Not within this region, like in any region outside of the hyperplanes. Not necessarily in the bounded one, in one of the bounded ones.
Do we have more questions for Dmitrii? I don't see any right now, so let's thank Dmitrii again.